Hey guys, this little video is going to show you how to do the couple of things that we're going to do from section 3.5. And our first topic is just a repeat of finding the domain, sorry about that, for a rational function. We are going to use this little example here that apparently I'm kind of attached to. We're going to change the instructions a little bit though. So for right now, just ignore what it says about finding the vertical asymptotes. We'll come back and do those in just a minute. But we are going to look at these in terms of what the domain of the rational function is. Now, just a little reminder about domain. We covered domain in section 2.2, and we actually did what I'm fixing to do again right here in exactly the same way there, okay? So what we have to do is we have to find all of the x's that will work for a particular function that won't cause any trouble. And in terms of a rational function, what would cause you trouble is a 0 in the denominator, so that's what we want to avoid having. And the way we looked for that is we set the denominators not equal to 0 to kind of drive home the point that we don't want them to be 0, and we solved them. And then whatever we found for that, we took those values out of the set. My pen's acting goofy. Let me scoot up a little bit, see if that helps any, of all real numbers. And we wrote it in interval notation because that's what WebAssign wanted. Okay, so we'll do that same thing here. Alright, so we start with a part, and for a, our function is x cubed over x squared plus 1. So what we're going to do is take the x squared plus 1, set it equal to 0. You will run into some quadratics in this section, so be sure you're ready for that. You may have to factor to solve. You may have to use the square root property, which is what we're going to use here. Or you may even need to use quadratic formula, okay? But you're going to have to be able to solve quadratics to do some of the problems in this section. Now, if I were to use the square root property, which works great for this because I've got the term that is the square, and then I've got just a constant term also. So what I'm going to do is subtract this constant term from both sides, and we get x squared, and what I was going to say I was going to do is supposed to be not equal to, sorry. X squared is not supposed to be equal to -1, and so we do the square root property, which makes this x equals or not equal to plus or minus the square root of that constant. And of course the square root of -1 is I. So we get plus or minus I. Now those are the points that would cause me trouble in my domain, but when we're discussing domain, we're talking about domain in terms of all real numbers. Well, imaginary numbers are not in that set, okay? So if you wind up with an imaginary number that's telling you you're having trouble with that number for the domain, you can ignore it because that number's not there to begin with, okay? We don't consider the imaginary numbers in these problems. Same thing goes for the vertical asymptotes when we do those in a minute. If you discover that your answer is an imaginary number, you just throw it away. We can't use it, okay? So we actually don't have a problem with any x value, since the only x's that would give us trouble would be imaginary. So our domain in this case is all real numbers, okay? And all real numbers is written in interval notation like this, negative infinity to positive infinity. Alright, let's move on and do b. Let's see, b was g of x is equal to x over x squared minus x minus 6. So this time the denominator, we'll set it equal, or not equal to rather, 0. This time we can factor that denominator, or you could use the quadratic formula if you'd rather here. I get a -3 and a +2. Set both of those not equal to 0 separately. And we get our two values that would make the denominator 0 if we plug them in. +3 and -2. So I've got two problem spots that I need to take out of the domain. And this is how we do that. No matter how many problem spots you have, whether it's one spot that you need to kick out or if there's like 16 different numbers, you start the domain at -infinity and you run this interval until you hit your first problem spot, okay? Now my first problem spot is the -2. That's lower than 3, so coming in from the left, you're going to hit it first. So we go from -infinity to -2. Then we stop our interval. We cut the hole at -2 by doing that. Okay, that's the exact symbols you're going to need to use when you cut your hole. You'll just change your numbers. Then you run again from -2 until you hit the next problem spot. Well, I only have one more, and that's the one that's at 3. So I run to 3. Stop that interval, cut a hole in it, pick it back up on the other side of 3, and I go on to +infinity from there because I don't have another problem spot, okay? And that's my domain with 2 holes cut. Now, if you've got 3 problems, just make another hole. If you only have one problem spot in the domain, then just cut one hole, okay? So that's just a repeat of domain that we've done before. Now let's take a look at asymptotes. They're very closely tied together. Because one of the things that can cause you trouble, and for some reason this is not wanting to let me lock it. Let me pause and see if I can. Okay, it just didn't like my pen. It didn't want me to use the pen on it. Vertical asymptotes are one of the two things that can cause those problems with the domain that we just saw a second ago. So when you find those domain issues, it's either going to be a vertical asymptote there, which is an imaginary vertical line in your that kind of shapes your graph. Your graph can get really close to it, but it won't actually touch or cross. Okay, and so what you wind up seeing is graphs that might look something like, let's say our vertical asymptotes right here. Maybe the graph comes in and swoops upward like that. And then from the other side, maybe it comes in and swoops downward. That's not the only shape they can take on, but that is one example of what happens around a vertical asymptote. They can't be crossed. To find them, it's a little different than looking for the domain, even though the problem spots in the domain can tell you where those are. It's not necessarily going to be a vertical asymptote there. It could be a hole instead. Now, most of the problems that y'all will work won't have holes. They'll just be asymptotes and you won't have to worry about them. But let me show you the process for finding a vertical asymptote. And this process includes a way that you can get rid of the holes, okay, so that you don't accidentally say that there's a vertical asymptote where there's actually a hole, okay? So, let me give it a header. It's real easy to do. The first step is to factor the numerator and denominator and cancel common factors. This gets rid of the holes. They would show up as factors in both the numerator and the denominator, so if you cancel them out, you get rid of them. Then anything that's left in the denominator, any other factors, you set equal to 0. Set any remaining factors in the denominator, equal to 0 and solve. And those will be your vertical asymptotes. They're written as little vertical line equations, so they're always written x equals constant. Okay, that's always the form they take on. Now, we're going to use these same two little things, and it's such a slight difference in how you find the vertical asymptotes in the domain that you may not notice much different about what we do with these two. That depends on the problem. Sometimes there's a lot of difference, like if you have to do some canceling and that kind of thing. Sometimes there's not much. Alright, so this first one if we look at it, I can't factor the denominator because it's the sum of two squares, it's not the difference. The numerator is already kind of factored because it's just x cubed. So there's nothing to cancel. There's no common factor between those two. So what I do is I just set the denominator equal to 0, and here again, just like I did a minute ago, I'm going to find that my vertical asymptotes are actually at imaginary numbers, plus or minus I. Since I can't graph those, they're not in the rectangular coordinate system, then I can't label them as asymptotes, okay? So what we say on a problem like this is that there are no vertical asymptotes. Alright, so then let's pick up B. Get it written down here where we can see it. And sort of the same thing happens. We can factor the denominator. In fact, I did just a couple minutes ago when we were working on the domain. And then once it's factored, you'll see that it won't cancel with the numerator. So there are no common factors to cancel. We still check that. And that means we set each piece equal to 0. About the only difference here is that I'm not using not equal to, because I do actually want the equation x equals 3 and x equals, negative 2. Those are our vertical asymptotes for this problem. And so if we were to graph this, we would find that graphing little vertical lines at negative 2 and positive 3 would help us to shape our graph. Okay, now I don't know much else about this by just glancing at the way it looks, but I can tell you those two things, that we do have those two vertical asymptotes there. Alright, and our last topic, very topic, drum roll please for the whole semester, horizontal asymptotes. Okay, horizontal asymptotes are like vertical asymptotes in that they do shape the graph, but they can be lost track of thought. They can be crossed. I don't know what I'm doing. They can be crossed. Sorry, they can be touched, but they aren't always. Okay, they still shape the graph basically the same way the vertical asymptotes do. They're just horizontal lines instead of vertical. Okay, there's not a lot of math, calculation math rather, that goes into finding a horizontal asymptote. What we use are these three little rules right here that I have grabbed out of your textbook. If you look at this looks kind of weird, but this is just a little rational expression, okay? And what the weirdo a sub n x on top, what that represents is the little polynomial on top, and then the b sub m of x is on the bottom. Those is a polynomial on the bottom, okay? So basically what you need to know from this in order to understand these rules is that we're calling the numerator, the degree of the numerator n, and we're calling the denominator's degree m. That's the important part here, okay? So if you recognize that, then this is not a big deal. You don't really need to know this part right here. Alright, so my first rule says that if n, which is the degree of the numerator, okay, if that's larger than the degree of the denominator, then the x-axis, which is the line given by y equals 0, is the horizontal asymptote, okay? So if degree on top is smaller than the degree on bottom, y equals 0 is your horizontal asymptote. If the degrees are equal to each other, then the line given by y equals a sub n over b sub m. Now don't make a big deal out of this. This is just the leading coefficient of the numerator, okay, see it right here, over the leading coefficient of the denominator. That's all that is. That's your horizontal asymptote. Okay? And then if the degree on top is larger than the degree on bottom, there is no horizontal asymptote. So those are the three rules you need. You can put that on the note card that I'm going to let you have for the final if you want to. Alright, so let's see what we've got here. If we do this first one, A part, f of x is equal to 2x plus 3 over x squared plus 1. What you need to figure out is what's the degree on top and what's the degree on the bottom. So the degree on top is 1, right? It's a little linear expression, 2x to the first. Degree on bottom is 2. Remember, degree is just the largest exponent in the polynomial. So degree on top is smaller. Okay? That goes along with that first rule. N is less than m. So what that means for us is that the horizontal asymptote, I'm going to abbreviate to make this a little faster, is going to be y is equal to 0. Okay? And then for B part, if you look at B, you'll notice that the degree on top and the degree on bottom are the same number. You got a degree 2 over a degree 2. They're the same. So we have the second rule where they're equal. And if you have equal degrees, your horizontal asymptote is y is equal to the ratio of the leading coefficient over the leading coefficient. So it's just the number in front of those 2 degree terms. 4/3 is what we get for B. And then C part illustrates our last rule where degree on top is larger. Degree 3 over degree 1. And in that instance, there is no horizontal asymptotes. Like I said, there's not really any calculation. You have to know a little bit of vocabulary because you have to know what the degrees are. You have to know what the leading coefficients are if you wind up with rule 2. And so that's what we get on that one. There's no horizontal asymptote on our last one. Okay? And that finishes us up.